So P is equal to 1 by 3 mn v RMS square, right? So I told you m into capital N divided by Avogadro's, sorry, this is number density, volume, v RMS. This is the total mass by volume. Mass by volume is density. So 1 by 3 rho c square. So instead of c, we use v RMS. Some books will use c. So 1 by 3 rho v square. So this is the important formula. So what did I say? I told you this is pressure. This is velocity. So as the velocity of the atoms or the molecules hitting the wall increases, right? So if it is kind of hitting faster, imagine the balls are hitting the walls faster, which means the wall is going to experience more force. More force means more pressure. So it means higher the velocity, higher the pressure. And instead of suppose if instead of a small plastic ball, right? If you had a huge ball like a rubber ball, the density like a cricket ball, then the density is much higher, which means when you get hit by a cricket ball instead of a tennis ball, right? It's going to be much more painful, which means higher the density, higher the pressure. Okay, so that's the meaning of this equation. And as I always say, this is your macroscopic and this is your microscopic. So that means what is happening in a microscopic level, that is what is creating a pressure in the macroscopic level. Okay, I hope you went through the derivation yourself. Okay, in the whatever we discussed in the class. Okay, little bit lengthy derivation, but nothing very difficult. Okay. Anybody having any doubts in this derivation? Siddharth, do you have this derivation in your textbook? Kumar and Mittal?
So I'm not sure, so I haven't gone through.
Opened your book.
Yes.
When I going to
Sir,
open your book?
Open, sir, but I haven't done it fully.
Okay. Remember, we are going pretty fast. Okay. We are in the last part of this syllabus. And we have finished waves and oscillations. We are doing the kinetic theory. So this is the last lesson now. We're going for theory. Of course, we have some numericals to do. Okay. So depending upon your school exams, we'll do the numericals. But first of all, I want to finish all the theory. Okay, coming back to this equation. I'm going to start from this equation. So P, I'm going to take the volume on this side. So PV is equal to 1 by 3 m into n into V RMS square. You see, half mv squared is kinetic energy, right? Instead of half, I have 1 by 3. So I'm going to do a little bit of adjustments here to bring it as 1 by 2. So what I'm going to do here is, from ideal gas equation, PV is equal to mu RT. That means in place of PV, I'm going to put mu RT. Why? Because I want to convert this pressure and volume in terms of temperature. Okay. Here I gave you a relationship. We are able to find a relationship between pressure and this one. So I'm going to bring this capital N on this side. 1 by 3 m v RMS square. Don't get confused by the term RMS, root mean square. Okay, so it's something like an average. Okay, you'll study this in your mathematics later, okay, in probability and statistics. So root mean square is something like how to say this? root mean square. Okay, this is square root, this is mean, and then this is square. So what you do is you take any quantity and you square it, and then you find the average, and then you take the square. That is what is called root mean square. There are some situations where taking direct average will not work properly. For example, velocities, right? So you have velocities in different directions. So if I take average, sometimes this velocity and this velocity will cancel each other, and we don't want that to happen. So for that reason, what we do is we take the numerical value and you square it, and then take the average. But then when you take the square and then average, you'll be getting the average of the square. So finally, you take a square root. So it's something like average. So don't worry too much about this. Okay, just for now, imagine that it's just average velocity. So as you study this in your mathematics, this will make more sense. Your 12th standard also will be studying root mean square. So R by N, I'm going to do mu by N. So mu somewhere else I told you N by Na. Number of moles divided by Avogadro's number is mu. I'm going to multiply and divide by 2. Why would I do that? Because I purposefully want to bring half mv square, because that is my kinetic energy. Nn cancels. R by Na is nothing but Kb, Boltzmann constant. Okay. R is a constant, Na is a constant. So R by Na I already gave you. Go back and check your notes. Okay. So R by Na is another constant called Boltzmann constant. This is your absolute temperature. This 3 by 2, 2 by 3 becomes 3 by 2 on this side. So that's a very, very important relationship. So this gives you the relationship between the speed of the molecules and the temperature. So what does this tell you? This is a constant, this is a constant. As temperature increases, the velocity will also increase. Or in other words, if the velocity increases, the temperature will also increase. So this is something like your kinetic energy of the molecule. Because m is mass of one molecule, so take it out properly. Small m stands for mass of one molecule. That means this is kinetic energy of a molecule. Okay, so as you can see, kinetic energy of molecule is proportional to the temperature. So that's what we are trying to prove here. Kinetic energy of a molecule is proportional to the absolute temperature. So again, the same story. This is your microscopic concept. Microscopic. This is your macroscopic temperature. Temperature is something like you can measure it. You can put a thermometer and you can measure the temperature of a gas, but you cannot tell the kinetic energy of a molecule directly, right? So you need to calculate it. So that's why I say this is microscopic and this is macroscopic. Okay, what else can I talk about here? 2 by 3. Any questions here? So in the previous derivation, we found the relationship between the kinetic theory and pressure. Okay. What is kinetic theory? Movement of molecules. What is movement of molecules? The velocity of the molecules. So we found a relationship between pressure and the movement of the molecules. So today in this derivation, what we are doing is we are trying to find the relationship between the movement of the molecules velocity and then the temperature. Okay, that's also for we are doing. Okay, there is one more derivation. Let's see, deduce Dalton's law of pressures from kinetic theory. This is what we derived in the last class, RMS, and V RMS square. This is your kinetic theory. Why do I call this as kinetic theory? Because kinetic means movement. So we're talking about movement of the molecules. Dalton's pressure, right? We are talking about different gases in one single container. So that means I'm going to write the total pressure as contributed by different gases. So M1, N1, V RMS square. M2, M2, V RMS square. So this is V RMS, V1 RMS. Okay, I forgot to write the V1 and V2. This is V2 RMS, okay, different velocities. I told you I'm going to write this as multiply by 2 and divide by 2. So it means I can write this as 2 by 3. N1 I'm going to keep it here. Then 1 by 2 M1 V1 RMS square. Plus same thing here. 2 by 3 N2. Then 1 by 2 M2 V RMS square. So this is kinetic energy of molecule of gas 1. And going very slow, okay, because it's not a very intuitive thing. So you have to understand the steps properly. Kinetic energy of molecule gas 2. So like that, I can keep on doing for next one like this. 2 by 3 N1 kinetic energy of one molecule at a given temperature, right? So this is a bit confusing. Everyone listen carefully. What we said here was kinetic energy of a molecule depends only upon the temperature. Why? Because these things are constant. So that means it doesn't matter within one single container. So pay attention, a bit confusing. So within one single container, let's say I have some hydrogen atoms. And let's say I have some helium atoms. So obviously you can imagine that in a given container, the temperature has to be same everywhere, right? You cannot say, okay, hydrogen is at 100 degrees Celsius and helium is at 50 degrees Celsius. That's not possible because the temperature will flow from higher temperature to heat will flow from higher temperature to lower temperature, such that everything will become the same temperature. So what I'm trying to say here is the temperature is constant here. So for a given temperature, the kinetic energy of the green molecules and the kinetic energy of the red molecules are going to be the same. Why? Because of this relationship. Kinetic energy of a molecule depends only upon the temperature. Okay, so assuming that the temperature is same, which has to be the same, right, in a given container. So take it down. In a given container, temperature is same for all molecules. So kinetic energy of the molecules is also same. Bit confusing concept. Okay, so what we mean here is the kinetic energy is same, but that doesn't mean that the velocity is same, because the velocity, there is mass and velocity. So if you take hydrogen and oxygen, the oxygen molecules are much bigger. So the green ones are much bigger, which means they'll be running slower, whereas the hydrogen molecules will be smaller, which means they'll be running faster. So it means m is smaller for hydrogen, whereas the velocity is higher. In the case of oxygen, mass is higher, but the velocity is smaller, but the kinetic energy is constant. That's what we are trying to say here. Definitely not an intuitive one, so make some proper notes. That means I'm going to say these things are constant, which means I'm going to say 2 by 3 and kinetic energy of molecules are constant. And what is left is N1, N2, N3. So after this, what did I 2 by 3 kinetic energy of one molecule? I can write this as 2 by 3 kinetic energy of one molecule. Just now we studied it as 3 by 2 kBT. So this and this will cancel. So KBT will remain. Anybody not following anything, please raise your doubts. KBT into N1. I need to go back to the basics. Let's see. N is number density, right? Number of molecules by volume. So listen carefully. You know that PV is equal to mu RT. N by NA. If the volume comes on this side, capital N divided by volume, R by NA into T, because volume has come on this side. Number of molecules by volume is nothing but number density. R by NA is Boltzmann constant. T is temperature. That means from your basics, you should know that P is equal to N kBT. So N into kBT of N1 will give me P1. N2 into kBT will give me P2. So anybody remember your Dalton's law of partial pressures from your chemistry? Anybody? You studied this or not? Nobody has studied this? Yes, no? Uzma, what did you say? Have you studied this in chemistry or not? Chemistry or
No, sir.
no?
Yes, sir.
Yes. Okay. So this is called Dalton's law of partial pressures.
It's basically when we have non-reacting gaseous mixture. So the total pressure of the mixture is in the summation of partial pressure of different component gases.
Okay, very good. So the very important word which he said was non-reactive mixtures. Okay, non-reactive. Why? Because if they react, then it will become some other molecule. So they have to be as separate gases. So if you have non-reactive gases, if you have this molecules, if you have some other molecules here. So the partial pressure of this yellow one and the partial pressure of the green ones, if I add them together, that will be the total pressure. P is equal to P1 plus P2. What do you mean by partial pressure? If I remove the green molecules and if I keep only the yellow one, what is the pressure? That is what is called P1. So the container is kept the same. If I remove the yellow one and if I put only the green one, that is your pressure 2. Now if I put them together, P1 plus P2 will be the total pressure. Okay, so that is what is called Dalton's law of partial pressures. Sum of the partial pressures. So these are the partial pressures. Okay. Any questions? So this is a derivation or deduced Dalton's law of partial pressures from kinetic theory, means this is what you're supposed to do. Okay. So as I always say, any derivation, you should know the starting point. If you don't know the starting point, obviously you cannot do that. So you should know the starting point and the ending point. Only then you will be able to do the derivation. Okay. I hope you are taking down the notes properly. Okay, I have not given all these derivations in your handbook. Okay, then there is something called Graham's law of diffusion. This is also something you have studied in your chemistry, I think.
Yes, so this is also, so this is coming in gaseous chapter.
Okay, so do you remember the law, Graham's law of diffusion? What is that you remember?
So Graham's law of diffusion basically, gas is inversely proportional to the square root of its molecular weight.
Molecular mass, very good. So rate of diffusion is inversely proportional to the square root of the.
So R1 by R2 is equal to the root of M2 by M1.
R1 by R2 is equal to root of M2 by M1. Yeah. So this is the law, rate of diffusion. Remember, this is not radius. Okay, this is rate of diffusion. So kinetic theory says kinetic energy of molecule is equal to d by 2 kBT. That's what we derive right now. Kinetic energy of a molecule. For a given temperature, just now I talked about this, so let's write it down properly. For a given temperature, kinetic energy is constant. So what does that mean? So I told you in terms of hydrogen and oxygen. So when the mass of the molecule is bigger, the speed will decrease because kinetic energy is same. So half mv squared is equal to constant. So what are we trying to say? Whether it is hydrogen or oxygen, for a given temperature at say 100 degrees Celsius, both of them will have the same kinetic energy. Okay. How is that possible? Oxygen has to be moving slower. Hydrogen has to be moving faster. Only then this is possible. Do you agree, everyone? No one has understood anything?
Yes, sir.
50 degrees Celsius, oxygen and hydrogen molecules will have same kinetic energy. However, oxygen having higher mass, so lower velocity. Whereas hydrogen, lower mass, higher velocity. Okay, so that's the meaning of this equation. Okay, so that's why I'm giving you a simple example. So now if I say V is equal to some constant divided by 2 into constant will become constant, m will come to the bottom and then square root. So it means this can witness. If that is not making sense, I'll give you one more step. 2 into constant divided by m. 2 into constant is some other constant. Square root, if I take it, I'll get V is equal to k root of K by root of m. If you say, sir, why you didn't put root k? Well, it's going to be another constant, so it doesn't matter. So now listen carefully. Again, you have to have good imagination. Suppose if the molecules are, suppose if I make a small hole over here, right, in the container, that's what we call it as leak, right? So if the molecules of the gas is moving slowly, then what will happen is by the time, it will keep on doing some random movement. And by the time it comes through this hole, right, it will be slow. But if it is kind of, very fast random movement, then what will happen is it will be coming and hitting this hole also very often, which means the gas will be coming out very easily. So what we are trying to say here is velocity of gas will decide how quickly it will diffuse. So don't get confused by the word diffuse. It's nothing but how quickly it can come through a small pore. So that means the rate of diffusion depends upon the velocity. So the rate, it depends upon the velocity. The velocity we found it as k by root m. That means the rate of diffusion is proportional to 1 by root of m. So it means what you can say here is space here, sorry, right. So take it down. So R is proportional to 1 by root m. So Graham's law of diffusion is proved, or we can say Graham's law of diffusion is a consequence of kinetic theory. So from kinetic theory, we are able to deduce Graham's law of diffusion. Anybody not following? So we are saying V is inversely proportional to root m, but rate of diffusion depends upon the velocity. This, if you are not able to imagine, I can explain it one more time. So let me show two cases. There is a container and there is 1 mm hole here. Similar container, same size, same 1 mm hole here. So here, let's say I have hydrogen atoms. So what did I say? Hydrogen atoms are doing random motion. The velocity is higher, which means it's not going to keep on running around here alone. Sometimes it will be hitting here. When they come in this direction, it's going to leak out here. When they come in this direction, it's going to leak out here. Are you able to imagine what I'm saying? Yes, no?
Yes, sir.
Yes, sir.
So now imagine that I have a little bit bigger molecules, which is oxygen. But let's assume that the leak hole is bigger than this size. Okay, so it's not about the size of the molecule which is stopped by this hole. So now instead of this velocity, this oxygen is moving a little bit slowly. If I show a small arrow mark, okay, from vector concepts, you know that the velocity is smaller compared to this. So when the velocity is smaller, how many times it's going to come in this direction? It's going to be very less compared to this one, which means oxygen will not leak very quickly, whereas hydrogen will leak very quickly. Okay, so take it down. Hydrogen will leak quickly. Oxygen will not leak quickly. That's all. Okay. If diffusion sounds confusing, just use the word leak quickly. Okay. Again, it's only for your understanding. In the exam, you have to write the correct word, which is diffusion. Both in chemistry and physics, you have to use the correct words. Okay, so we talked about kinetic theory relationship with temperature, right? The earlier class we talked about kinetic theory relationship with pressure. Today we talked about kinetic theory relationship with temperature. Then we deduced Dalton's law of partial pressures using kinetic theory, and now we deduced Graham's law of diffusion using kinetic theory. Okay, so far we have done 4 different derivations. How to find speed of molecules. If temperature is given. So very often, somewhere in your numericals, this will be useful. Kinetic energy is nothing but half mv square. Is equal to 3/2 kBT. So this again, to remind you, it's mass of one molecule. So let's take the example of nitrogen molecules in atmosphere. So you know that air is consisting of 21% oxygen and 79% nitrogen by volume. So I know this value, I know this is a constant. Mass of one molecule is known, which means I can find the speed of the molecule itself. Mass of one molecule, how do I find it for nitrogen? Well, I know that nitrogen is mass number is 14. For nitrogen gas, it will be 28, right? So 14 plus 48, 28U. So 28U is the molecular mass, right? So this is mass of one molecule, so 28U. So U is nothing but 1.67 into 10 power minus 27, right? So if I do the math, I will be getting, so you know this, you know this, you know this, which means you can find this. So very often you'll be using this for your velocity calculation. So lighter the molecule, higher the speed. Why? Because when this is smaller, this will be higher. Okay, so far what we have seen is kinetic theory and then different derivations, right? Pressure, temperature, Dalton's law, Graham's law. Next topic is law of equipartition of energy. So take it down. In equilibrium, the total energy is equally distributed in all possible energy modes, with each mode having an average energy equal to half kBp. This is known as the law of equipartition of energy. So what are they trying to say? In equilibrium, right? Meaning the temperature is same everywhere. So if you take a container, the molecules, so there are different modes of energy, right? So let's talk about those things first. So the molecule might be moving this way in the x direction. It might be moving in the y direction, or it might be moving in the z direction. So you have something called translational energy modes, which is x, y, z. Okay. And then the molecule might be rotating in a particular axis. So if the molecule is something like this, let's say you have x-axis, and if I say something like a dumbbell, so if it's rotating like this, I can say the molecule is rotating about x-axis. Let's say this is y-axis. So if the molecule is rotating about y-axis, right, then it would be looking something like this. Again, it's three-dimensional, a little bit difficult for me to show it in 3D. And if you consider the z-axis, imagine that I have a dumbbell like this. If I'm rotating like this, that's your z. So the molecule is rotating about z-axis. So it means you have, this is called translational mode of energy transfer, sorry, translational mode, and this is called rotational mode. There is one more mode which is called vibrational mode. Okay, in the same place it can be vibrating instead of moving or instead of rotating. It can just keep moving up and down. So this is called vibrational. So take it down properly. Translational energy mode. This is rotational mode. This is vibrational energy. This is, we don't have any proof for this. Okay, for now, of course, this right now for your higher secondary level, they are not given this proof. Okay, but maybe if you take physics in college level, you will be studying the proof. Okay, so this is outside the scope of this textbook for now. So without proof, we are taking that if I take the total energy, right, the total energy is equally distributed in all possible energy modes. So I told you what are the energy modes. So you have XYZ translation energy mode. You have XYZ rotational energy mode. So with each mode having an average energy equal to half kBT. So each mode will have an energy of half kBT. So within translation, you have half mv square, right? It can be moving in the x-axis direction. It can be moving in the y-axis direction. It can be moving in the z-axis direction. Right? Rotational, we studied something called rotational system of particles, chapter 7, right? So what is a rotational kinetic energy? Anybody remember? List of mass, what should I put here? This is linear work, this is rotational work. So what should I put? In place of mass, I should put. Nobody remembers?
Omega.
Omega. Mass equivalent. Velocity equivalent is omega. What about mass equivalent? Already forgotten. Moment of inertia.
I.
Okay. Moment of inertia in x-axis and omega x square. Similarly, half Iy omega y square. Similarly, half Iz to omega z square. Inside the vibrational mode, right? Imagine that it's something like a spring. It's kind of moving up and down. If you are wondering why I have shown it like a dumbbell, right? Sometimes it's something like a hydrogen molecule, right? H and H, O and O, something like that. Okay. So vibrational energy mode is for one mode, within one mode, right? For within one mode, what happens is when the spring is going up and down, right? You have some velocity and you also have some potential energy. Okay, so this is a bit confusing, so pay attention. So when it is moving up and down, right? So for one vibrational energy mode, right? You will be having something called potential energy, and then you will have something called kinetic energy. As the spring is moving up and down, there is kinetic energy, and then there is something called potential energy. Half kx square and then half mv square. Why dy by dt? Anybody? What is dy by dt? This is your displacement, right? In the oscillation, displacement is y. So half k y square. So if it is displaced more potential energy. If it is displaced less potential energy. What is dy by dt? Everybody sleeping? Okay. Keep on moving. I know it's a very dry subject. Okay. I don't have a choice. So I need to make sure that if you have any doubts, I can explain it. Nobody seems to be interacting. It's very depressing for me. At least in a offline class, I can see your faces. Here I can see it. Anyhow, I will keep moving. Okay, do whatever you want to do. I will keep doing my duty. This is potential energy. This is kinetic energy. So what I'm trying to say here is there are three different things. One is translational, one is rotational, and then one is vibrational. Okay. So within translational, you have X, Y, Z. Within rotational, you have X, Y, Z. Okay. You can rotate about X-axis or Y-axis or Z-axis. And within vibration, you have kinetic and potential energy. So what this says is each one is the energy mode. So this is one energy mode, this is another energy mode, this is another energy mode. So each energy mode will get an energy of half kVt. Okay. But in the case of vibration, what will happen is this will get half kVt, this will get half kVt. So totally it will become kVt. So for one vibrational mode, within one vibration mode, you have both kinetic and potential, which means you'll be getting kVt. So for this mode, I will be getting half kVt. For this mode, I will be getting half kVt. So that means for one vibration mode, I will be getting half plus half 1. So it will be getting kVt. Energy for one vibration mode. Okay. In all the other cases, I'll be saying this is half kVt, half kVt, half kVt. Okay. Similarly, here also I'll say for this I will get half kVt, half kVt, half kVt. And that's what law of equipartition of energy says. Each mode will get energy equal to half kVt. In some molecules, we will be assuming that it is moving in all the directions. But so suppose if I take monoatomic gases. So listen carefully, very simple, nothing difficult here. If I consider monoatomic gases, such as helium, so you're going to show only like this, which means it can be moving in the X direction, it can be moving in the Y direction, it can be moving in the Z direction. Okay, but if you consider the rotation about this axis or this axis or this axis, right? What happens is the molecule is very small. So since the radius is very small, we kind of ignore that it doesn't have any rotational mode of energy. Okay. So it's not going to have any rotation. Then when will you have rotation? Suppose if you consider diatomic gas. Something like your hydrogen, oxygen, nitrogen. So these kind of gases, you can imagine something like a dumbbell. So this is one atom, this is another atom. So it can be moving the X direction. It can be moving in the Y direction. It can be moving in the Z direction. At the same time, it can rotate about the x-axis like this. It can rotate about the z-axis also. But in one of the mode, right? Again, this is very, very easy for me to explain if it is like a face-to-face class. I don't know how to explain this. Let's see. Let me switch on my video here. So let's see, I have some kind of a dumbbell. I have a dumbbell inside the classroom. Just a minute. So that's a dumbbell, right? So imagine that this is one molecule, one atom, and this is another atom, right? So if I am moving it this way, right? This is x-axis, this is y-axis, and this is z-axis, right? So it means you have three translational mode of energy transfer, right? Energy modes. So suppose if I keep it like this, listen carefully. If I am seeing it from this side, x-axis, it can rotate like this. That means it's going to have some rotational motion, which means it can have a rotational mode of energy. If I see it from the top, from the z-axis, it can rotate like this. Say that again. The video is stuck. Can you see it now or not?
Yes, sir, it's on.
So if you are rotating like this, let's say this axis, right? So if I'm rotating like this, then it's rotating about z-axis, okay? Which means here also you will have a significant rotation, okay? Rotational mode, moment of inertia will be significant. But look at this, if you are seeing it from here, right? How many circles? So Chaitanya, I think only you are saying the video is stuck, all the others are okay. So maybe it's your net connection. Okay.
The video is on, so.
Yeah, but is it getting stuck?
No, sir.
Okay. Then I think it is Chaitanya, it might be your net being slow. So look at this. Right now in the video, right? What do you see? Do you see one circle or do you see two? Can you see that, you know, behind this is kind of hidden? Now you can see two. Here you can see only one, right? So suppose if I'm rotating like this, again, you know, I have to be very careful. I think it's like 5 kg. If I drop it on me, it's going to be dangerous. So suppose if I'm rotating like this, right? When you're rotating like this, the rotational moment of inertia is significant. When you're rotating like this, it is significant. But if you're rotating like this is not significant. Why? The radius is very small. Here the radius was this big. Here the radius is only this much. So because of this reason, in diatomic molecules, right, what happens is we will be considering only two rotational mode. We will not be considering this rotational mode because this radius is very small. Anybody not following, please raise your doubt. I cannot hold this for a longer time. Okay. So take it down properly. When you have the dumbbell like this, right? When you are seeing it from the x-axis, this is significant rotation. When you are seeing it from the z-axis, this is also significant because this radius is bigger. Okay, which means I is equal to mr squared. So if the radius is bigger, moment of inertia will be bigger. But suppose if you consider this as your y-axis in this direction. Suppose if you are turning it like this, you see the radius is very, very small. So since the radius is small in this direction, we say that the diatomic molecules will be considered only for two rotational motion, and this one will be ignored. So only this alone is neglected. These things are significant. What did I say about the monoatomic gas? In every direction, you see the radius is going to be smaller, which means all the rotational modes are neglected. Okay. I'm just trying to go a little bit slow. Okay, you have to understand these concepts very well. Only then you will understand why it is neglected. Okay. So with that background, I think we can do a small derivation very quickly. And if you go to triatomic, right? So we talked about monoatomic, diatomic. Now it is triatomic. Triatomic, for example, is something like, there are different types of triatomic gases. So if you take hydrogen, H2O, right? Like steam, for example. Sorry if I do it. So H2O, which means there is only one oxygen molecule. H2O. So that's a triatomic. But if you take carbon dioxide, right, CO2. So this is called a linear triatomic. This is not linear. This is non-linear. You can say not linear. So if you consider linear triatomic, it's very similar to the diatomic. Okay, why? Because the rotation about the x-axis and the rotation about the z-axis will make sense. But if you see it from the side, the rotation about this, right, it will be, to take it down, similar similar to diatomic. Only two rotational modes considered. Plus 3 translational modes. What do you mean by translational modes? X, Y, Z. Whereas here, when it is triatomic, right? What it means is, let me switch on my video one more time. So triatomic means, imagine that I have one more molecule here. So now rotating this side is also significant. Rotating this side is also significant, right? And now if you see it from here, rotating this side will also become significant. Why? Now the radius is this big. So you have one more atom here, which means the radius is here. Which means as I'm rotating about y-axis, this will also become significant. So that means in a non-linear triatomic atom, you will be considering the third rotational mode also. Anybody not following, please ask right now before I close the video. Anything not clear? Ashwant following? Ashwant, no answer. Okay. So in triatomic, you will be considering 3 modes of translation. 3 modes of translation. And 3 modes of rotation. So this is the starting point. Okay. So only if you understand this monoatomic, diatomic, triatomic, why we are considering, why we are neglecting some of the rotational modes and why we are considering, sometimes we are considering the rotation mode. Only then the later topic will make sense. Okay, just a sec. Let me connect my power. Okay, let's see. It's already time. I'm going to give you a small self-study homework. We'll discuss this. Of course, I'll discuss this in the next class. But I want you to try this. I've given you the basics. So I've given you a nice table in the handbook. So go to page number 36. I thought of completing this today, but again, as I always say, I don't want to rush through. So as far as possible, I want to go in a proper speed, proper pace, so that if you have any doubts, you should be able to clarify it. Waiting for the PDF to open. Let's see. So I want you to take it as a homework, like a challenge. Okay, so try this yourself. Okay, so I've given you everything nicely, something which is given as some, say, 3 or 4 pages in your textbook. I've given it in one single table. So I want you to try this. Okay, so you see monoatomic. Monoatomic means you don't have rotational or vibration, so it's only translation. So try this after this. 3 times half kb. If it is diatomic or linear triatomic, what did we say? We'll be considering 2 degrees of freedom for rotation, 3 degrees of freedom for translation. Here we are assuming no vibration. So 3 plus 2 will be 5. 5 into half kb. So this, go back and study, try to understand where these things are coming from and take this as a formula. Once you are able to do the first one, all the other things are very, very easy. So 3 by 2 RT CPC. This is for one, so note it down properly. KB, whenever you see KB, right, it is for per molecule. So you see I have given it in the bottom. Whenever you see R, R stands for the mole. So that means U and R for per mole. E and KB are for per molecule. So all these things are very, very confusing in your textbook. Okay. So I tried to give all these things separately, properly. Okay. So once you get that and then go back to your thermodynamics, look for the relationship. So do this as a simple challenge. Okay, challenge homework. Try this. Once you do the first one, all the other things are easy. Okay, so next class I should be able to complete this. So this should not take more than 5-10 minutes. Then this will take another 5-10 minutes. So hopefully we should be able to finish this in the next class. With that, the theory will be over. Okay. So then I'll try to do some numericals depending upon your. We'll discuss how many of you are having school exams, and then we'll plan accordingly. Okay, thank you all. If you have any doubts, stay back. Otherwise, you are free to go. Thanks.
Thank you, sir.
Thank you, sir.